Okay, so now that we have our local version of this project running, meaning we have our app locally sending a prompt um, over to our Gemini API and getting an API response back, we need to start thinking about conceptually what can break this app in production. And I have some idea. Obviously, you never release an app on local. You need infrastructure to handle traffic, right? But for the sake of working with these LLMs, I started to ask Gemini what some of the challenges could be, and just go through the whole process with Gemini, the whole thought process with Gemini. And so it gave me two things. You might be able to guess what they are, but one is concurrency and throughput. So the process meal scan function in Scan Coordinator is the most resource intensive part of the app. The 6 p.m. rush. If 500 parents all scan a meal at 6 p.m., you may hit an AWS AppSync default quota, typically 1,000 requests per second or Lambda cold start delay. So essentially, what this is for my non-technical people is you're trying to get about 500 people through one doorway at 6 p.m. That doorway being your database, because your database has to actually save your Gemini responses as analysis records in Scan Coordinator, and then those analysis records populate our infrastructure for our gauges, right? So if I'm trying to put 500 parents through that infrastructure at one time, it's not going to work. So I want to start to work with Gemini on how to configure my infrastructure to solve these specific problems and to scale this app. And this is the beginning of that process. So I asked, how do you fix this? And I mentioned the things that Gemini had mentioned earlier as far as concurrency and throughput and the 6 p.m. rush issue. And so it came back to fix the concurrency and throughput risks in your process meal scan function during high traffic periods like the 6 p.m. rush. You should transition from a synchronous request response model to an asynchronous event driven architecture. This is big, right? This is the backend architecture that's going to allow you to separate functions that individual users or groups of users do to access the parts of the database that they need to, that the app needs to access, but to do it in such a way where they're not all going through the same door, and you also configure sort of those doorways, to stick with the analogy, um, to function together in such a way that they themselves don't create any conflicts. So let's walk through what it told us. Decouple processing with async mutations. Currently, your app waits for the entire Gemini analysis and database write to complete before the UI can proceed. To fix this, you should separate the request initiation from the heavy lifting. Modify process meal scan to simply upload the image to S3. That makes sense. And trigger a mutation that starts the process. The AppSync resolver should immediately return an execution ID or success status to the client, allowing the parent to continue using the app while the analysis runs in the background. So the analysis functionality of process meal scan becomes, or is decoupled from the actual app thread, and the app is still running in the background. That's essential. Real-time updates, app sync subscriptions are something that you can use to notify the app once the background processing is finished. The app listens for a specific child ID or session ID and updates the dashboard charts automatically when the data is ready. So what we do is we pass, like, we know the child ID, or we know the session ID, or we even have the analysis ID, right? We could create the analysis ID. Once I press scan, there's no analysis object, right? There's no iron, potassium, magnesium. No, Gemini hasn't given us any response yet, but we have, I shouldn't say there's no object. There is an object. That's what we're saying. But there's no object data, right? Gemini has not returned any data yet, but we create an object that is essentially an empty object with our analysis ID or with our child ID or whatever ID we choose to use for that object. And the charts sort of wait for Gemini to respond for that particular ID. So our system knows that we just made a scan for analysis ID 0001, and then we create some kind of listener for specifically 0001, analysis 0001. And when analysis 0001 is updated by our Gemini response, then because we have a listener engaged, that information populates and propagates to our UI so that it shows on our gauges. And this makes perfect sense, right? Anyone who has worked with infrastructure before knows that you want to split things up. You want to have asynchronous functions, and you want to have some kind of trigger for asynchronous functions that need to reflect immediate or near immediate changes in your UI for your users. Number 2, mitigate Lambda cold starts. If hundreds of parents scan at once, AWS will spin up many new Lambda instances, leading to cold start latency. I think this is also assuming that we move our scan coordinator functionality out of scan coordinator into a Lambda function. So scan coordinator is a local function that runs on Swift. If you know anything about cloud computing or Lambda, AWS in particular, Lambda in AWS is an extremely fast tool that you can use in AWS to run functions. You can run Node, you can run Python, you can run JavaScript, but you use a Lambda function to actually execute some code that interacts with your database, interacts with your S3, interacts with different parts of your backend quickly and cleanly. So it's assuming that we would use Lambda. I think that's a healthy assumption. If hundreds of parents scan at once, AWS will spin up many new Lambda instances, leading to cold start latency, right? So if we just create a Lambda function, every time we have users, AWS is going to spin up multiple Lambda instances, and it takes effort to spin those instances up, right? It's like spinning up compute. It's like spinning up a virtual machine. It's not a virtual machine, right? It's not EC2, but it requires effort, and it will create latency. So what our Gemini is recommending is provision concurrency. This is the recommended solution for predictable low latency. Keeps a specified number of execution environments warm, so it spins up Lambdas that kind of just sit there warm, waiting for users to use them. Warm and ready to respond instantly, eliminating the 500 milliseconds plus initialization delay during traffic spikes. This 500 milliseconds doesn't sound like much, but if you're talking about hundreds or thousands of people, it accumulates. And so provision concurrency becomes, essential. Optimize memory and runtime, increasing your Lambda's memory allocation to 1,000 megabytes or higher proportionally increases the CPU power available, which can speed up both the initialization and the intensive AI processing logic. Lightweight runtimes like Node.js, Python, or Rust generally offer faster cold starts than Java or C. Yes, so you heard me mention just now Node or Python. Those would be the things that you would want that are more performant and still extremely powerful. Java and C are, good for certain use cases, just not this one. You often see Node and Python in a lot of consumer-facing apps now because of the speed and still, ability to handle some pretty compute-intensive workloads. To protect your AppSync and DynamoDB from being overwhelmed by a sudden burst of 500 plus concurrent requests, queuing. This one is new to me, or at least it's something that I have worked with in terms of technical debt, but as far as setting it up, it's new, and I was glad to learn that this is exactly how to do this from beginning to end. But instead of a direct resolver to Lambda call, have your AppSync mutation send the image metadata to an Amazon SQS, simple queue service queue. A Lambda function can then poll the queue and process meals at a controlled rate that stays within your API quotas and budget limits. AppSync caching enables server-side caching for your resolvers to reduce the load on your data sources or for repeated or frequent requests. So if you can imagine, of course, let's say we distribute our our prompt function or our processing meal scan function into a Lambda. And we know that if we don't have provision concurrency, spinning up multiple Lambdas for multiple users is going to create latency. So we add provision concurrency, and of course, just having the Lambda and having our processing our meal scan as an asynchronous function, it decouples usage of the app from processing the meal scan. So that's all good. The challenge becomes that if I have, again, multiple people, even with all of that infrastructure, if I have multiple people using the app, the processed meals can still pile up, right? So I might have multiple provision concurrencies running, but if I try to run them within a certain time period of each other, then the rate that we hit with our API, right? Not anything to do with AWS, but if I try to run a certain number of Lambdas that then call Gemini, right? Then that's gonna impact. If I try to run a certain number of those in a certain period of time, let's say 500 people want to go all at once, and our infrastructure handles that. But let's say we get up to 600 or 700, our infrastructure handles that. But then the API quota for Gemini starts to say, okay, you're pinging Gemini too much, right? So we need some queuing. We need a buffer zone queue that moderates the rate of, our sort of, I won't say unlimited, but our less limited infrastructure that, allows us to ping our API as much as we want to. We need to limit that with a buffer, which this simple queue service can provide. And that buffer will ultimately control the rate, the maximum rate of Lambda instances that hit our Gemini API, so that we won't go over our Gemini API quotas and budget limits. So that's very good. These are all very, 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 very good things to get from Gemini, particularly on what amounts to a first pass. We didn't have to do very much. We did establish good context in terms of our app, what our app does, what it's attempting to do, our use cases. Prior to this, I specified, what happens at 1,000 users, 5,000 users, 10,000 users, to get Gemini in the frame of mind, thinking about the operational burden that different levels of users can cause. And this ultimately is the fruit of that. But what this becomes is a very comprehensive framework for our backend, and it's given us a number of AWS items. We've already committed to AWS Amplify, which sets up CloudWatch and DynamoDB for our database and a few other things, and synchronizes them. So we don't have as much work to do as far as synchronizing our AWS backend. That's handled. But as far as what we're configuring and what the purpose of that is and what our scaling strategy is, this information is invaluable, and it will determine exactly how we use our process meal scan infrastructure. And if we determine that we want to add any other back-end functionality that should not be exposed on the client side, that needs to sit on our server side, this infrastructure model provides a way for us to do that in parallel with our process meal scan functionality. So, the sky becomes the limit as far as what the app can do, and we can allow the market need to dictate where we go from here, if anywhere, beyond our current strategy. Next, I went to ask, can you define provision concurrency? And so we get our definition here. Provision concurrency is an AWS Lambda feature that pre-initializes a specified number of execution environments, keeping them warm and ready to respond immediately to requests. So pre-initialization, it downloads your function code and starts the runtime. Pre-execution, it runs any initialization code located outside, and then it sustains a hyper-ready state. It maintains these environments so that it can respond double-digit millisecond latency, very quick. Let's see, what else did we have here? So then what I did was I started going into how would you do this? And this is something that I really love when it comes to Gemini and all the LLMs is, I don't know about you guys. I'm a product person. I'm code literate, but I hate technical documentation as written on the internet, right? I love writing technical documentation because I try to make it as clear as I possibly can for the audience that I can, write it for. But I hate reading documentation on some site for a service because it tries to be so inclusive that it ends up being, very very light on definitive access points or pathways that you can go through. So in asking how would you do this, I can get from LLMs specific plans that are interactive to tell me where to go. Go to the Lambda console, which is a console in AWS. Select your function, choose publish new version, create an alias, add a configuration, set capacity. And these directions are accurate, extremely accurate. Occasionally, particularly with AWS or probably any cloud compute group, one thing will be slightly out of place. There may be a missing step, and either I'll find it myself, or if I really can't find it, I'll put a screenshot and say, add configuration isn't on the next screen, and it'll say, oh, it looks like it's updated. Try this, try that, and eventually I find add configuration. But I can get a step-by-step on exactly what's going on or where I need to go to implement these things. So provision concurrency, I get a formula around what exactly what I'm buying, so I can figure out exactly how many instances to set. And I think later on in here I talk about the cost associated with concurrent instances. This is one of the most expensive AWS features, but it's worth it if you have an app in production to always have your Lambda available. Automated scheduling, cost optimization is here as well, which I don't think I ended up using just yet. But this is valuable, really valuable stuff. And we have a video here on YouTube of someone who's actually configuring Lambda, a tutorial much like the tutorials that I'm creating here, although probably from an engineering perspective, so a little bit more detailed. So that's great that we're in a good place. For me, I wanted to keep going and keep challenging Gemini about exactly, additional use cases and additional issues. So another one was data integrity and race conditions, which it brought up previously as well. So a race condition, let's say I've got, 10,000 users, and I do have the functionality right now of multiple parents sort of sitting on a family account, and they can see their kids, right? You've got, mom and dad scanned breakfast, mom is now looking at lunch, right? And so what happens if they make a change at the same time, or they try to do something to the same child's meal object or analysis object? And so race conditions with 10,000 users, the chance of conflicting rights increases. If a parent tries to update a child's age on two different devices simultaneously, your current raw mutation might overwrite data without checking for version conflicts. And then app sync limitations is a separate issue. App sync has a default limit of 100 results per query, while fine for a single family. If you ever need to fetch all children in a school group, you will need to implement cursor-based pagination to avoid missing data. So these are additional infrastructure solutions or considerations that Gemini is bringing up based on the other concepts or potential risks that it gave me earlier when I prompted and asked for scale-oriented risks. So to address the scalability risks of 10,000 plus users, you must move from simple CRUD logic to robust distributed systems logic, optimistic currency control for race conditions and cursor-based pagination. Solving race conditions, enable versioning. Turn on versioning for your DynamoDB data source. And I didn't know how easy it was to actually turn on versioning in DynamoDB in the AppSync console. AppSync will automatically add a version field to every record and increment it on every successful write. Set the conflict resolution strategy which is another feature in AWS, to optimistic concurrency. The client, this is how it would work in the app. The client, your app, fetches the current record with its version. When sending the update mutation, the client must include that version. AppSync checks if the DB version is still v5, which is what the first one was. If it matches, update succeeds and the version becomes v6. If it doesn't match, if there was let's say the last version was v5 and this person is v7 because the other parent is actually doing v6 right now, but they don't know it. If it doesn't match, AppSync rejects the mutation and returns an error with the current server-side data on the app, so that the app can merge the changes and retry. So at that point, what we can do on the app side is send a message and say, oh, it looks like the other parent was making a change at the same time. Do you want to let them do that, and then once that's done, we'll show you the current state, or we just kind of like let that one finish and propagate through, and then that's what they see. And along with the message that says it looks like the other parent was doing something. This is what they did. Do you want to still make your change, or maybe you say, oh, well, the other parent was doing it. Let them do what they needed to do. But at least you understand what's going on as the user, and we're not just overwriting things blindly. AWS, as it does many things well, has the infrastructure already in place to do something that, as an app developer or a product team, you would want to do in a lot of cases with multiple users on the same account, which is version control. AppSync's default 100 user or 100 result limit is a safety guard to prevent long-running queries from timing out. To fetch all children in a school group, you must use next tokens. So this is giving us another pre-built sort of element that's part of AWS that we can configure for a mass AppSync query in the event that we do have a situation where we want schools to be able to, maybe share school lunch and plug that into the app, and it sort of propagates to all the families that are associated with that school, and then they have the option to bring that school lunch in and see that school lunch's impact. Maybe they have the option to select of the 2 or 3 things that school lunch served, either send the kid a text or manually ask them, what did you eat from the school lunch? They had pizza, they had a cheeseburger, and they had hot dogs today. Which of these things did you eat? And once the kid tells them, then they just select from the 3 things. But the key is, if we're doing that database function of pulling more than 100 limits or more than 100 items out of the database, then we need this cursor-based pagination feature, and we get a full description about how to use it. So, I asked a few other questions, but this is probably, this was something that I expected, or I did not expect would be as high quality a response as it was, and it really was. But it was because prior to this, we set the groundwork, and we described, that descriptive prompt is really important. We described an issue. Prior to this, we said, if we have 1,000, 10,000, 50,000 users, what are the scaling issues that we're going to run into with this app that's built purely on local now? We got a response back, and then based on those responses, we asked for a specific definition of how we would fix this within the context of AWS. We're already, we've already established that we're working in AWS, and that we have AppSync, which comes standard with Amplify. We already established that. So what we got was a really high quality response because we laid the groundwork. So now that we have some pillars to build our infrastructure model around, we're gonna take process meal scan out of our local, out of our Swift app, because you never want to put your prompt in your Swift app anyway. People can decompile that and then see it, right, if they know how to code. So we're going to take it out of our Swift app, put it into a Lambda, configure the Lambda to run asynchronously with the app, add provision concurrency, add SQS queues for throttling, and then add, we mentioned provision concurrency, and then also add the other two elements. Pagination, we haven't really added a school functionality yet, but we're going to add, let's go back down here, add our race conditions for optimistic concurrency for parents on the same account as well. So very good progress. Let's keep going.